Imagine buying an electric car with a range of 500 kilometers. Then winter arrives and suddenly your dashboard shows only 350 kilometers. Is the battery damaged? Not at all. The real explanation is hidden inside the battery chemistry, thermal management system, and even the weather itself. Let's dive into the engineering. Inside the lithium-ion cells that power your EV, energy flows through a straightforward chemical process. Under normal operating temperatures, lithium ions travel back and forth between a graphite anode and a metal oxide cathode through a liquid electrolyte. But when the temperature drops, this liquid electrolyte thickens and the entire process slows down. Imagine trying to swim through honey instead of water. The lithium ions struggle to travel through the sluggish liquid, which dramatically spikes the battery's internal resistance. In plain terms, the battery has a much harder time pushing energy out, reducing both its maximum power output and the total available energy. This performance drop is completely temporary and does not mean your battery is permanently damaged. Once the cells warm up to their standard operating temperature, their full capacity returns. The exact impact of this cold weather slowdown depends heavily on the specific battery design inside the vehicle. Most modern electric cars use one of three main chemical compositions: nickel manganese cobalt, NMC, nickel cobalt aluminum, NCA, or lithium iron phosphate, LFP. Battery chemistry deserves its own dedicated video because every chemistry has different strengths and weaknesses. For example, LFP batteries are highly popular because they offer a long cycle life, excellent safety, and lower manufacturing costs. Yet, LFP chemistry experiences much more noticeable low temperature performance reductions than NMC or NCA. At minus 20 degrees Celsius, an NMC or NCA cell can retain over 70% of its capacity, while an LFP cell under the exact same freezing conditions typically drops to around 55% of its rated energy, making thermal management an important system part. While driving in freezing temperatures temporarily reduces performance, plugging a cold battery into a high-powered fast charger introduces a far more serious hazard: lithium plating. Under normal conditions, lithium ions slide cleanly into the microscopic layers of the graphite anode during charging. But when the battery cells are cold, this insertion process slows down dramatically. At temperatures below freezing, even moderate charging rates can overwhelm the anode. If forced to charge too quickly, the incoming lithium ions cannot penetrate the graphite quickly enough. Instead of intercalating safely, they begin to pool and build up on the surface of the anode, transforming into a physical layer of metallic lithium. This plating permanently robs the battery of active lithium, which over time reduces overall capacity and raises internal resistance. In extreme cases, these metallic deposits can grow into tiny needle-like structures called dendrites, which can pierce the internal separator and create severe safety risks. To prevent this damage, the vehicle's battery management system acts as a protective shield, aggressively throttling charging speeds when plug-in temperatures drop below freezing. We'll dedicate an entire episode to lithium plating because it's one of the least understood aspects of battery aging. To counteract this cold weather performance drop, electric vehicles deploy an active defense system: battery thermal management. Instead of leaving the pack to freeze, the vehicle's onboard computers continuously run software algorithms to monitor and adjust cell temperatures, attempting to keep the battery in its sweet spot of 15 to 35 degrees Celsius. This begins with preconditioning, which uses grid power while plugged in to preheat the battery before you even start driving. To generate this heat, many EVs rely on high voltage electric heaters. These resistive elements warm liquid coolant that is pumped through circuits directly touching the battery modules. While highly effective, resistive heating draws a massive amount of electrical power. This is why manufacturers increasingly turn to heat pumps. Rather than creating heat, a heat pump moves existing thermal energy from the ambient air or the drivetrain into the battery. For example, Tesla's octovalve system links the motor, inverter, and battery into a single loop, scavenging waste heat from the electronics to warm the cold cells. Hyundai's Ioniq 5 takes this further with a dual loop heat pump system that achieves a coefficient of performance of 3.5, delivering 3.5 kilowatts of heat for every single kilowatt of electricity used. BMW's i4 and Mercedes-Benz's EQS use dedicated liquid coolant plates and battery tray heaters, routing heated glycol water mixtures through the pack to prevent frost formation. Warming the pack is especially important before direct current fast charging. When you navigate to a high-power charger, Tesla, BMW, and Mercedes systems automatically trigger active heating. Bringing the cells to 30 degrees Celsius before plugging in ensures rapid charging speeds and protects the anode from degradation. Throughout this process, software continuously fine-tunes the thermal valves, balancing cabin warmth with battery safety to squeeze every mile out of the pack. An internal combustion engine is highly inefficient, losing about 70% of its fuel energy as heat. In winter, this waste is a free source of cabin warmth. Electric vehicles, however, are highly efficient, meaning they must create cabin heat intentionally. This direct link between comfort and energy consumption means keeping your passengers warm directly drains your driving range. Older or simpler electric vehicles use resistive heaters, which convert electricity directly into heat with a coefficient of performance of 1. This means 1 kilowatt of electricity yields exactly 1 kilowatt of heat, draining up to 45 watt-hours per mile. Modern heat pumps, however, act like reverse air conditioners, moving thermal energy from the outside air into the cabin. This delivers up to 3 or 4 kilowatts of heat for every kilowatt of electricity used, saving up to 50% of heating energy and preserving valuable range. Cold weather also alters how your electric vehicle slows down. Regenerative braking is simply charging the battery while driving, reclaiming kinetic energy during deceleration. But cold lithium-ion cells cannot safely accept high charging currents without risking lithium plating. To protect the anode, the battery management system caps regenerative braking power. When you lift off the accelerator on a freezing morning, the car will decelerate much slower because the battery is protecting itself, not failing. When temperatures drop to minus 10 degrees Celsius, the air itself becomes 10% denser, increasing aerodynamic drag and forcing the motor to expend up to 3% more energy just to maintain highway speeds. Below the chassis, cold air contracts the tires, dropping pressure by 1 pound per square inch for every 6-degree drop. This drops tire pressure, causing rolling resistance to surge by over 30% on cold rubber, which worsens on slushy or snowy roads. These external forces stack directly on top of the vehicle's internal thermal losses. This is where the gap between different EV designs widens. An older, air-cooled Nissan Leaf with a simple resistive heater can easily lose 30% of its range in freezing conditions. Meanwhile, a modern electric vehicle using an advanced heat pump and active liquid thermal management can restrict that winter loss to just 10%. To protect your winter range, simple adjustments to your daily driving routine go a long way. Start by preconditioning the cabin and battery while plugged into the grid. This warms the vehicle cabin using house power. saving your battery's energy for driving. When planning to fast charge, always route to the station using the car's built-in navigation, which automatically warms the pack to the safest possible temperature before arrival. Inside the cabin, rely on the heated seats and steering wheel to stay comfortable as they draw a fraction of the energy required by the high-voltage climate control system. Make sure to check your tire pressure every single week to combat cold air contraction, which directly spikes rolling resistance, and avoid fast charging a freezing pack unless the vehicle has already warmed the cells. Winter range loss is not a design flaw, but a reflection of physics. As technology evolves, these cold weather boundaries will shift. We go far beyond simple EV news into battery chemistry, solid-state systems, and the engineering behind the future of mobility. Subscribe for more deep dives.